In another video, we learned about the difference between accuracy and precision. In this video, we're going to zero in on precision, and specifically, we're going to talk about something called significant figures. This is a way that scientists deal with the fact that there's lack of precision, there's uncertainty in all of our measurements, so that we can report that to the people who are reading the numbers that come from our measurements. So significant figures are just a way of reporting the precision of our measurements. It's kind of sophisticated. It's built into the way we write our numbers, and it's not like an extra note that has to be added on to tell anybody about the precision of the tools and the measurement systems that we're using. To get an idea of how this works, let's think about trying to measure this purple object with this measuring stick that's the yellow object. How long is the purple thing? Well, we don't have any markings on this stick, so the only thing we can do is look at one full stick, and in our mind, mentally, we can divide it into pieces. And we always think in terms of decimals in science, because most of the time we're using the metric system, which is a decimal-based system. So that's kind of the mindset to get in. I'm looking at this, and in my mind, mentally dividing this up, I think this is about 3/10 of a stick. I would estimate that the distance from here to here is about 3/10 of the way, and then the other 7/10 of the way would be to the end of the stick. So I would record that as 0.3 sticks. And remember, you want to include a unit in measurements because we don't want just naked numbers in science. Now the 0 here isn't really necessary. I just put it in front of there to kind of reiterate that this is less than 1 stick long. What I have done is I've written down a number that has one significant figure. The 0 is not significant. I don't really need it, and it's not really part of the measurement. So I have recorded that 0.3. That 3, that digit there, that's what we call a significant figure or a significant digit. Let's measure that same purple object, but now with a different stick. This time we have a more sophisticated stick. It's got a marking every 10th of a stick. So I can now read this with more precision. If I think about this value here, this is going to be 2/10 of a stick, and this is going to be 3/10 of a stick. So now I know that since I have a more precise tool, it's not really 0.3 sticks, it's somewhere between 0.2 and 0.3 sticks. And in my mind, I can now divide this into 10 segments. I can read this to the 10th as well. And it looks to me like it's 8/10 of the way between 2 and 3. And so I would say that the length of this purple thing is 0.28 sticks. Because this tool gives me greater precision, I now can write this number to 2 significant figures. So the significant figures are all the numbers we know for sure, plus one more digit to the right that's kind of a guess or an estimate. So I know the tenths part for sure. There's no question about that. This purple thing ends after the 2, but before the 3. But this one here, well, that's a question mark. You might read this and say, no, it's more like 0.29, or you might say, no, it's more like 0.27, but nobody would say it's 0.26, and no one would say it's bigger than 3. And so we would have our uncertainty in that last digit. So it's all the digits you know for sure, plus you add one more that's an estimate. And that's how we always read. That's the greatest precision that we get. In this case, that results in 2 significant figures. Same purple object, only now we have an even better measurement tool. Let's zoom in a little bit so we can read this better. So now with this tool, this is 0.2 sticks, and this is 0.3 sticks, and we have 10 markings in between. So each of these is a 1/100th of a stick. So right here, this value, well, that's 0.2, 5, 6, 7, 8.28. And this marking here is 0.29. So now I know more about my measurement. I know that my value of length of the purple thing is somewhere between 0.28 and 0.29. So the 2 digits I know for sure are the 2 and the 8. That's a for sure. And now I have to estimate. How far does the purple thing reach between 0.28 and 0.29 in tenths? So a tenth of 100th is 1,000th, so I can read this to the nearest 1,000th. When I read this, I say that the length of this is 0.288 sticks because I'm thinking that it's 8/10 of the way between 0.28 and 0.29. Again, these are the 2 digits I know for sure. Everybody agrees 0.28. But this one, that's where the uncertainty is. You might look at that and say, no, it's not 0.8, it's 0.7, or you might say, no, it's 0.289, but very few people would go much lower than plus or minus 1 from that last digit. So this measurement, because of our increased precision, gives us 3 significant figures. So the more significant figures you have, the greater is the precision of your number. So we spent a little time here talking about how to write our measurements, how to make our measurements and record them. Now we have 3 rules so that we can properly read other people's measurements. Let's take a look at that. So if you look up on the internet or look in some textbook or something like that, you might find a whole series of rules, 5 or 6 different rules for reading measurements. But really you can narrow it down to just 3 rules. The first rule is zeros that are between a non-zero digit and an implied decimal point are not significant. So let's look at an example to get a better idea of what I'm talking about here. Let's say we have this measurement, 120 with a decimal point after it. This decimal point here, that's not implied. Implied means it's sort of hinted at that it's there, but it's not really there. This decimal point is actually expressly written down. So all of these digits are significant. In other words, what the measurer is telling us is they know the 100s place for sure. It's bigger than 1, but not as big as 2. They know this place for sure as well. So the hundreds and the tens place are for sure. By putting the decimal point there, they're saying to us, that thing there, that 0, that's not just holding the place. It's actually where my value is, my last digit that I'm estimating. So they're saying it might be 121, it might be 119, but for sure it's plus or minus 1. So that's 3 significant figures. If the measurer has written this down with no decimal point written, so in other words, there's an implied decimal point there, it's not really there, that's a way of reporting to us the precision of the measuring tool. So this person is saying, I know the 100s place for sure. It's bigger than 100, but it's not as big as 200. But I don't have the ability to directly measure for sure the tens place. And so that is where the variability lies. So they're saying it could be as low as 110 or as high as 130, and I have no idea what the ones place is with my measurement tool. So that last 0 there is between a non-zero digit, the 2, and an implied decimal point, one that isn't actually written. And so only the 2 first digits are significant. There are 2 significant figures here. This number, written the way it is with an implied decimal point, is telling us that we have only 1 significant figure. This is saying that those last 2 digits, those are just placeholders. They have to be there because 1 and 100 are totally different numbers. But they're telling us that the variability occurs at the 100s place, that they only have the ability to measure plus or minus 1/100 with the measuring tool that they have. So that's the first rule. Zeros that are trapped between a non-zero digit and an implied decimal point, that's one that's not actually written, are not significant. The next rule says that zeros to the left of a non-zero digit are not significant. This statement actually has a little bit of an error in it. This should say zeros to the left of the first non-zero digit are not significant. So if you have this measurement, 0.288, that 0 that comes out there, that's just there to show that this number is smaller than 1. It's not significant. So that's 3 significant figures. All the non-zero digits are significant there. In this case, there are some zeros that are before that first non-zero digit that are actually after the decimal point. This is a little bit harder to understand why those zeros are not significant, but all of those first zeros will not be significant. Now, they have to be there, but they're just there to hold place. And the significance of our measurement starts actually at the 10,000ths place. So this is the digit that has our variability in it. And these digits, well, they just hold that place. If they were not zeros, they actually would be significant. But in this case, they just serve as a placeholder. This is the most confusing of our rules. So it might be useful to just kind of memorize it and say, if you have zeros that come to the left of the first non-zero digit, those are not going to be significant. The last rule is really easy. Any digit that isn't part of those first two rules is significant. So if we look at this number here, we have zeros that come to the left of the first non-zero digit. Those are not going to be significant. So not significant part of the measurement, not significant, not significant. This 5 is going to be significant, and non-zero digits are always significant. And this 0 will be significant. How do we know that? Well, for one thing, it's not the kind of 0 that fits into the first two rules. It doesn't come to the left of the first non-zero digit, and there isn't an implied decimal point after it. But another way you can think about this is, there's got to be a reason that whoever wrote this measurement down didn't just stop at 5. They were trying to tell us something by writing that extra 0, is they were trying to say, I know this digit for sure. I know the thousandths place for sure. And this, well, that's that estimate. That's that extra digit. So they have the ability to estimate the 10,000ths value in this measurement. This next one has got 3 significant figures. This last 0 is not a significant digit. It comes to the right of a non-zero digit, but to the left of an implied decimal point. So there's a decimal point that could be there, but it's not written there for a reason. And that's because the measurer who's telling us this information wants us to know that they know the thousands place for sure, they know the hundreds place for sure, and their variability, that decimal that they have to estimate, that comes at the tens place. And so the ones place is just a 0 that holds that place. Because again, 102 is a different number than 1,020. So the 0 is necessary to be there, but it's not a significant part of the measurement. And only the 3 significant figures to the left count in the measurement. This last one, this 0 that's in the middle, it does not come to the left of the first non-zero digit, and it is not to the left of an implied decimal point, and so it counts. And so in this case, all 3 of those digits are significant digits. Lots of times in science, especially in chemistry, we end up with numbers that are very big and very small. And when those are the case, it makes sense to write numbers in scientific notation. So the format of scientific notation is always some number m times 10 raised to some number n. This number here is called the mantissa, and the mantissa is always greater than 1, but it's less than 10. So it's greater than or equal to 1, but it's less than 10. It's always in that range in scientific notation. It also includes all the significant figures. So if you're writing in scientific notation and you know how many significant figures you have, you put those numbers and only those numbers in the mantissa. This thing here is called the exponent. That's the other part of it. And sometimes that's a negative number when the number is smaller than 1. When it's bigger than 1, that n's going to be a positive number. So you've probably heard about exponential notation, or our specific case of that called scientific notation in the past. That's how that works. But the important thing for precision is all of the significant figures end up in the mantissa. So there's 2 sig figs in this number, 1 significant figure in this number, and in this number, which is actually a famous number in chemistry, there's 4 significant figures in that number. So now you've learned how to write your measurements using significant figures to properly report the precision of the measurements that you're taking. You've also learned 3 rules so that you can read other people's measurements and know the precision of the tools and devices and practices that they were using to get their measurements. Significant figures are an important way that sophisticated science communication tells us about the precision of our tools without having to explicitly write notes that describe that. So it's a very handy tool, and we use it all the time in science to report the precision of our measurements.